Data structure using C++, Module 4, Session 3. Previous class we have discussed few properties of binary tree. There are 4 properties which are very important. Next, let's look at how to represent a binary tree in using arrays. So the topic to discuss is sequential representation, or it is also known as array representation. How the elements present in a binary tree gets a valid position in an array. That's what we will be discussing. Now here, as addressed long back, complete binary trees, if you are working with, then to some extent the wastage of the memory, if you are using arrays to store the elements present in a binary tree, then total number of spaces which gets in vain will be lower. Suppose if you are working with the incomplete binary tree, then you can figure out that many spaces will go in vain. More number of spaces you will be wasting. So incomplete binary tree has a disadvantage. So waste space here addresses only if you are working with the incomplete by complete incomplete binary tree. So this is an example of complete binary tree. So complete I call because when you look at the last level, level 4, we have deleted E is not having it is a terminal node. E, F, G are terminal node, and suppose if there was a right child present here and not a left child, then I would have called this as a incomplete binary tree. So the rule is in this level, so the last level we are not giving more importance. The fourth level, all elements while filling ensure that the left child is not deleted prior to right child. So suppose if there was one element being the left child of E, I was not having any problem. I would have called this tree still as a binary, complete binary tree. But suppose if E is having a right child, then it violates the rule saying that the priority for right child is given more. So right child is not deleted, rather we delete left child. So first right child should be deleted, then the left child for any node when you're deleting any elements in the previous nodes. So last node you cannot delete. So that's what is binary tree, complete binary tree is. And also we have seen the rules, probably the rule for checking. This is actually the rule which you need to follow, which elements can be deleted. So it is based on this rule which we have discussed. Now here, when you look at this, we can scan so how this elements gets positioned in an array. To discuss that, you have to scan from level wise. So this is your level 1, level 2, level 3, level 4. Level 1 elements, element by element you push it onto this array from left to right. While scanning, move from left to right. So top to bottom you need to traverse, and left to right element should be moved on to this array. So first level element is A, second level elements are B and C, they get filled. Third level elements are D, E, F, G, so it is also filled in the same order, D, E, F, G. And last level H, I, so this H, I you have. So when you observe this array which has been pushed using some method, so all these elements, none of the spaces are empty here. None of the spaces are empty, all are filled in a proper manner. Now suppose if the situation is you have an incomplete binary tree, you call this as an incomplete binary tree because level 5 you have, level 4 elements are destroyed, level 3 elements are not there, level 2 elements are not there. So it violates some of the rule addressed by the complete binary tree, and you call this as a left skewed tree, left skewed tree. So this is a main node which is having a left child, this node again has a left child, C has a left child, D has a left child. So everywhere right childs are absent, this is not having a right child. So when you store this data in this memory location, so first level A goes here, second level B and C you have, but this is actually the space for the right child, so that is empty because you don't have element. Similarly, when you look at the third level, so if all elements gets its right child or left child, so you will be having, if I'm not wrong, level 3 you will be having 4 elements. So in level 3 only one element is there, so 3 empty elements. Fine. Similarly, when you're moving over here, so fourth you have 8 elements, out of which only one is filled, so remaining 7 are not filled. So that's how it is. And finally E is filled, so you can figure out this dot means there are many elements from 10 to 15. Those many number of elements are not at all used, memory is not used. So you're wasting much space. So this will be the situation only if you're working with a incomplete binary tree. Complete binary tree as such, you don't have any issues as such. So let us see two more examples. So this is a complete binary tree. We call this binary tree as a complete binary tree because you're in level 3, and level 3 you can see right child of this tree is deleted. Suppose if 6 was, even if 6 is not there, not at all a problem, you still call this as a complete binary tree because the elements gets filled in this order: 1 2 3 4 5. Okay, so even 6 if it's deleted, no problem. So you can remove this 1 2 3 4 5, you have complete binary tree. Similarly, this is also complete binary tree. So sequentially all elements gets loaded in the array. Even this is a complete binary tree. So there is no space, there is no wastage of space when we are working with complete binary tree. So this is an example of incomplete binary tree. 2 examples. So A, B, C, D, get many spaces are wasted here. Finally, this is also incomplete binary tree. We call this as an incomplete binary tree because you're in level 3. Level 3, when you look at B is not, its left child is absent, whereas right child is present, so that breaks the rule. So priority is give priority for the left child. Left child should be there, right child you can ignore. You can delete the right child, then you can delete the left child. So here left child is deleted, then you have a right child, so it violates the rule. So this is an incomplete binary tree, and you can figure out that there is a space in between, gap is there, so wastage of memory will be there. You are working with incomplete binary tree. So this is how we talk about the concept or representation for binary tree. This is not that acceptable because we have seen literally the situation you will not get always complete binary tree. There is a chance that you may get incomplete binary tree. So in that case you will waste much memory location. So that is not which is a good technique. So instead we can move with the linked representation. So how the node structure will look like if you are following the linked representation. In the linked representation, this is a better way to represent a binary tree. So here as we know, the node for a linked representation for a binary tree, you know how many elements a node will have. So each node, which we call a circle, which we put if of this form, so it will be having a value, and also you will use 2 pointers. One pointer points to one node and another pointer points to another node. Suppose if this was a node named A, and we can say that A is pointing to B and C. If it's told us, then we say that B happens to be a left child of A and C happens to be a right child of A. So since we want to construct the pointers, the structure of the node for a binary tree would have this 3 information: data, which is actually the node element, value of the node, left child. So when you're constructing this, and ensure that this arrow mark talks about it, this is a pointer. This node in turn points to some other node. So this left child should be a pointer type, which can point to a binary tree node. So rather than calling it as a simple node, we call this as a binary tree node of a binary tree. So binary tree node. Similarly, right child is also a pointer which points to some other node, right? So rule which we follow, you can take this, but this is not that important. The textbook defined terminologies you can use. So this program is the node structure for a binary tree, important. So we have seen chain node. We can relate this binary tree node with chain node structure. Chain node is actually the simplest node for node creation for linked representation. So we had chain node with the three terminologies: chain node with no arguments, chain node with one argument, chain node with two arguments. So here, I guess in the same manner, we have here binary tree structure is not chain node, it is struct binary tree node, and this is having element, that's the node value, and its data type can be anything. We can have integer, we can have a character, anything. Similarly, these are the three constructors which we have here, and these are the variables. So we are using three variables: element, node pointer. This is a binary node pointer, left child and right child. So star left child, star right child, both are pointers, pointing to binary tree node. So we use star left child and star right child because this has to match this. Here it should be a pointer, this is also a type pointer type. So both are pointers here. Fine. So this is your first constructor. The first constructor job is to write the binary tree node with no argument. So this binary tree node doesn't have any argument. So left child as well as right child, in this case left child and right child are set to null. So that is to say that creating a binary tree node. Second form of binary tree node with element. So second form, it takes a element, binary tree node with the element, and this one has to in turn take the element, load it into the element component of this binary tree, and the left child and right child of this particular binary tree, we make it as null. I repeat, the second instance of binary tree node takes one argument, and it is going to set the left child and right child of the binary tree to null. The third instance of binary tree node takes all three components: element, left child and right child, and here the user entered value, let's say that we are supposed to construct the name of this node is A and its left child is B and C. So in that case, we are supposed to pass the arguments, the value which needs to be which needs to be sitting on the node A. A is a node, has to have a value, say 10. 10 is actually the element present in the node A. So the element value would be 10, and this should point to, so you will write 10 here and you'll write B and C, which means the left child of the current node A is B and the right child of this current node is C. So you have the node A value 10 and its left node is B and it's pointing to right node which is C. So for that we use this form. This is used more often. Most often this is actually the terminology used for building the binary tree node structure. Hope this is clear. So explanation is given here, which I have already addressed. You can have a look at this. Now let's look at the various traversal or common binary tree operation. What and all operations your binary tree should consist. So some set of operations which your binary tree while constructing the class binary tree should handle is to find the height of a binary tree. This is one thing. Determining the size of the binary tree, so which is nothing but number of elements present in a binary tree. Determining or displaying all elements present in a binary tree, that would also be required. So for this you have various traversal technique. We will talk about it in a while. Then you have to check whether the two binary trees addressed are equal, and also the to check, you can figure out this, make the tree empty. How do you delete an element from a binary tree and make the tree empty? So all some of the operations which are essential when you're building a structure named binary tree. Hope this is clear. So this is to some extent a theory question. Next is very important, binary tree traversal. So we will not talk about the program today. We will discuss how the equivalent expression for various traversal technique. So the more common traversal technique which we have addressed in the syllabus are in order technique, post order technique, pre-order, and one more is level order. So in order technique, the way we traverse, give priority to left first. L implies left, V implies visit the node. After left, then node, then right. In post order, it is left, right, and visit. Left, right, and node. Meanwhile, in pre-order, it is node, left, right. So follow this terminologies when you're traversing the complete binary tree. I repeat, in order, which was already discussed, left, node, and right. So expression tree for displaying the expressions, or for designing the expression from a binary tree, we had followed in order technique. So there, left tree was scanned first, followed by the root, then right subtree. In post order, it is left subtree, followed by right subtree and a node. Pre-order, it is the node first, followed by left subtree and right subtree. So this are traversal method. Along with this, we have level order based on the levels. Suppose if you are having 4 levels, scan the first level, all elements from left to right you can display. So those happens to be the level order technique. Okay, so we will discuss one example, and we will see what will be the expression generated using all these orders: level order, in order, and pre-order. So let's take an example. This is an example. The expression, a binary tree is given to you, and we are working with in order. So in order, so as addressed, traversal technique, left, visit, and right. So this is your left subtree for this binary tree. First priority is given to left subtree, followed by the root or visit or node, followed by the right subtree. So 1, 2, 3, this is actually the priority given. So what you have to do, scan the left subtree first. Okay, in left subtree, again recursively you have to scan. So in this left subtree, again find the left subtree of this tree. So the left subtree of this tree is A. So that is actually the first element which gets outputted. So you write A first. Then we use, after scanning the left subtree, we go to the node. So for this left subtree, the node is plus. So we write after A, plus comes. So after A you have plus. After visiting the node plus, then comes the right subtree. Now you have A plus B. So we have done with this. So this priority subtree is completed. Then go to the node. So after that, go to this node. So you have A plus B followed by slash. So after completing this, then visit the right subtree. Now this is the last priority given to this subtree. Now here, while scanning again, you have to remember this order. Traversal method, left, visit, and right, root, right. So left for this tree, left is C, then minus, then D. So left subtree, root, and right subtree. So C minus T you write after slash, C minus T. So this is an example how do you write an expression given a binary tree. Already this was discussed. So next one, we will look at pre-order situation. If it's, then what will be the expression generated for this binary tree. So what is the method? So first, give importance to the node. So this element should be written first, the node, and recursively you have to follow. So first, the element in this node comes first, slash you write, followed by the second subtree. This is your second give priority for this left subtree is 2 now, so you have to visit this subtree. So while visiting this subtree, again follow this root left and right. So root of this left subtree is plus, write that, then the left it is A, then the right it is B. So this is scanned completely, the elements are already displayed. Then visit the right subtree, again follow this root left and right. So root minus left C right D. So ultimately we'll be getting this expression. So traversal method, VLR, visit left root. Visit means node root. The third order is post order method. In post order method, it is left, right and visit. So this is the priority one, left, right and node. So in left, that is this tree, left subtree, while visiting first left, right and node. So what will be the value? A, B plus. I repeat, in the left subtree, the traversal terminologies which you need to follow here is LRP. So left, right and visit. So A, B plus. So I write it A, B plus. Then we go to right subtree now. So in this again, right, left, right and node. So you write C, D and minus, C, D minus. Finally, go to the component which is having least priority, that is the node. Element is slash, so it is displayed. This is your post order technique. So left, right and root, left, right and visit. The last order is level order. So here you have to, the approach is from top to bottom, and while moving from top to bottom, scan all the elements from left to right. So if this is the given binary tree, the first topmost level, the element is slash, so it is written first. The second level, elements are plus and minus, it is written next here, plus and minus. Third level, elements are from left to right, it is A, B, C, D. So it is written A, B, C, D. This is an example of various traversal method. Right? So one more example, if it's required, you can work on this expression. So you have A by B. So this is actually the binary tree which you have. So you're supposed to work with in order. So in order, so we go from left, right, left, node and right. So first we pick the priority for left subtree. This is that left subtree, give highest priority for left subtree, followed by root, then the right subtree. So first in this left subtree, again break this into its left subtree. So this left subtree, if I consider it as a tree, its left subtree comes out to be this. So this will be the left subtree of this tree. If I consider, again we are in this position now. So in this position, again take its left subtree. When you take the left subtree of this tree, that is the star slash CAV, its left subtree becomes this A slash B. This becomes the left subtree of the tree star, this tree. Okay, so when you're over here, again take its left subtree. When you take the left subtree of this tree, if it's decided as, then you ultimately go to this element. So A is actually the first element which gets displayed. Then continue, go to the because this is valid binary tree, you have all elements, you can traverse properly. After A, slash B comes, slash B it is written, then B, A slash B is done. So once you are completed with this left subtree, go to its node, root, so that is star, so it is written next. Then its right subtree, C is written. Then again go to the next level, or else previous level, so there it is star. Then again its left right subtree value, so it is D. Then again move back to the node, main node, plus, then finally its value, so E you have. So in order is written, expression is written in this form. Level order is simple. So plus we write first star E, second, then we have star D, third level, fourth level slash C, last level AB. This is easy, very easy to understand. Pre-order. So in pre-order, what we do, node followed with left, right. So first, this is actually your node, this is your left subtree, and this is your right subtree. So first node value is plus, so plus is written, then go to the left subtree. In this left subtree, again follow the order, node first. So what is the node of this subtree? Star. So write that. So you have a star coming in. Then again go to the next subtree, left subtree. So this is the left subtree which I'm considering. Its node you consider. Again you have star, so it is addressed here. Okay, then again its left subtree you consider. So this will be the left subtree. It pick its node, that is slash. So slash is taken. Again take its left subtree. So that is A. So in this you take the node. So you get A. Then you write after moving this, you take B. Right subtree you take. Then again C. This is done. Then again D. Then again E. So this is how you follow. So first we started with the node, all nodes were considered. Then when we moved on to the bottom, then we scanned all the right subtrees. That's the procedure for post order in the same way. So it follows left, right, and node. So left, right, and node. So this is the left subtree. You have a right subtree, then finally the node is here plus last it comes. So left subtree, what should be displayed here. So this left subtree again has to be decomposed into a left subtree, which happens to be this. Again this left subtree has to be decomposed into this. Again this when it is decomposed, you get A. So A will be the first data, which is correct. Then we go to B, then slash. So AB slash, this completes this tree. Then we move on to C, then star, then D, then star, then E, then finally E. So that's how you address postfix. Time being, we will wind up the class. We'll see the traversal method program in the next class.